Hey guys! Welcome to the second part of our TwinCAT 3 Ninja Monkeys tutorial, where we'll dive deeper into our candy vending machine project.
In our previous video, we set up the initial project structure and explained what we have in mind. If you did not watch the first part, click in the upper right corner of this window to start with the linked video. For everyone who has already watched the first part, now, we're ready to bring our candy machine to life.
Let's get started with some sweet automation. Alright Yeknom, we've got to build this candy machine structure, but I think we should start by making an abstract base. Let's call it AbstractCandyMachine.
Good idea. So, an abstract function block, right? That way, we don't implement the actual candy logic here, just the structure.
Exactly. We'll define the overall framework, like the method to get a candy. But we'll leave it abstract. Each specific machine will have to define how it works. First we create two folders, first one, Candy Machine, and second one, Classes. In here we create the AbstractCandyMachine function block.
Okay, done. Now, we'll need to add a method to get a new candy. We can call it getNewCandy. This will force each candy machine to implement its own logic for dispensing the candy.
Yeah, it should take the preferred candy type as input. But remember, it's just a placeholder for now. We won't actually define any candy types here.
There we go. Now any machine that extends this class will have to provide its own logic for what candy it gives out.
Right, but here's something we'll want to keep in mind. Each machine might have its own valid candy types, so we need a helper function to check if the candy type is valid for that machine. Let's call it IsCandyTypeInvalidForMachine.
Yeah, and this method should be protected. It's only for internal use by the machine, not for anyone calling the machine from the outside.
We declare a variable called CandyType of type CandyTypes. Perfect. Now, we just need to add the logic. The check here should ensure that the candy type is within a certain range and that it's a power of 2. That bitwise trick, using the AND, for checking powers of 2 should do the job.
Got it. So first, we return true if the type is outside the range, right?
Good. Now, for the power of 2 check.
Okay, that works. But now that I'm thinking about it, wouldn't it be slimmer to use conditional returns instead?
Yeah, you're right. Let's clean that up. Much better. Now the logic is easier to follow. So we've got the base of our abstract candy machine. This class doesn't deal with specifics, but it sets the rules for any candy machine that gets built on top of it.
Yeah, now the real work will be implementing those specific candy machines. But this gives us a solid, flexible foundation to work with.
Exactly. Now we just need to ensure any derived machine properly implements getNewCandy and does its own validation through IsCandyTypeInvalidForMachine. And with the legal notes added, we're done for now.
Alright Ajnin, let's set up the consumer types enumeration. It's simple, it covers the key consumer types we've been talking about, common, greedy, and picky.
Looks great. The qualified-only attribute means we'll always need to use the full name ConsumerTypes.common, ConsumerTypes.greedy, and so on. No ambiguity here, which keeps things nice and clear.
Yeah, no room for surprises with the strict attribute either. It ensures that only these exact values are used for consumer types, so if someone tries to pass an invalid number or string, they'll get an error.
We also need the toString attribute, which allows us to easily convert these values into readable text, which could be useful for logging or displaying information to users. Alright, Yeknom, I will also set up a new enumeration, called TasteScale. This will help determine how satisfied our consumers are with the candies they get. It's pretty simple but covers all the necessary cases: disgusting, okay, and delicious.
I like this. It's a nice touch to have a taste scale that works directly with the consumer's satisfaction. So, if the candy is disgusting, it reduces their happiness, and if it's delicious, it boosts them.
Exactly. I make OK the default value here because it feels neutral. If no specific taste is defined, it won't affect satisfaction one way or the other.
I see, you set OK as the default by writing dint equals OK. Nice touch. That way, if the candy doesn't specifically make someone happy or upset, it'll just leave their satisfaction level untouched.
Yes, and that default behavior is important. You don't want every candy interaction to force a change in satisfaction, especially when it's not meaningful. Now let's create 3 folders. First one, NinjaCandyBehavior, because that's what the enums are for. Second one, types, and last one, enums. In there we put our enums.
Well, Ajnin, looks like we've just added 3 new candies to the collection. Each of them extends Abstract Candy and has their own unique initialization through FB init. This setup feels smooth and dynamic. This looks good. Poppins is being initialized as a hard candy with 18 grams. I like the use of the ColafterInit attribute. It ensures that the candy is set up correctly before we start using it. And of course, Enable dynamic creation means we can create this candy on the fly as needed.
Here, M&M's candy is initialized with 45 grams and categorized under chocolate candy. The same attributes are used here, making sure it can be dynamically created and correctly initialized. The ColafterInit ensures everything is set up before usage, just like the other candies.
And finally, we've got the gold bears with 75 grams. These fall under gummy candy. This setup is consistent across the board, making all our candy objects easy to create and manage dynamically. Ajnin lets build a machine tailored for those picky consumers, just like yourself. This PickyCandyMachine can dish out a wide range of candies from Snickers bar to Skittles sour. We can use the new operator to dynamically allocate the specific candy based on the candy type's input.
Yes. I want to make sure that we can handle all the candies the picky consumer could want. This getNewCandy method dynamically creates the candy objects only when requested, which keeps things efficient. First, we create pointer to the different candies in the var section, because the new operator requires a strictly typed pointer. And at the end a pointer to AbstractCandy, its return value is just a candy. Now I will start to implement the code for the machine. The method first checks if the candy type is valid by calling isCandyTypeInvalid for machine. Then, based on the candy type input, we dynamically allocate the corresponding candy using the new operator, which gives us the correct candy object.
Yep. The case statement is handling all the different candy types. Once the correct candy is created, it gets assigned to the candy pointer. The final steps ensure that the candy is initialized with its dispatchers before it gets returned. You've got a lot of dynamic creation happening here, which is great for flexibility. But one thing to watch out for: what happens if the system runs out of memory for all these new allocations? You might need to handle memory management carefully.
That's true. I've added the check return, candy smaller equals 0, to ensure that the candy pointer is valid after creation. If the memory allocation fails, we safely return without causing issues.
Overall, this is a well-designed candy machine for picky consumers, Ajnin. You've thought of everything, from dynamic allocation to error handling. Okay, Ajnin, now it's time for my GreedyCandyMachine. Unlike your picky machine, mine doesn't care about getting the best match to the requested candy type. Instead, my machine is all about getting the biggest amount of candy possible. If a type can include multiple candies, it will go for the largest option available.
I see you've structured your machine similarly to mine, but there's a key difference. For certain candy types, you're combining multiple candy categories together, like CandyTypes.CandyBars and CandyTypes.ChocolateCandy, and prioritizing bigger candy selections, like Snickers bar.
Yep. Greedy consumers don't care as long as they get more. When the input matches certain types, like candy bars or chocolate candy, the machine gives them a Snickers because it's the biggest chocolate bar. The same happens with CandyTypes.Gummy Candy and CandyTypes.Licorice Candy. They'll get Twizzlers because they offer more volume than other gummy options.
You've also kept the error handling in place, similar to mine. The machine checks if the candy type is invalid using IsCandyTypeInvalid for machine, and you've also included the memory allocation check with return, candy equals 0. Smart move.
Yeah, no need to let the machine crash if it runs out of memory or the candy type is invalid. Greedy, but still careful. It's all about getting the biggest bang for your candy buck, Ajnin. Greedy consumers will never leave disappointed with this machine. A third candy machine for the common candy lovers, huh? Nice and straightforward, like a standard go-to for the masses. We've already covered the logic for the picky machine, so this one should be a breeze.
Right, no need to reinvent the wheel. We're just adding another layer. Since we already extend the AbstractCandyMachine, the structure is there. What we need to focus on is balancing the selection based on the common consumer's preferences.
Exactly. The common folks don't need any fancy restrictions, unlike the picky or greedy consumers. This machine should just dispense candies in a way that's generous but not overboard.
Looking at the Get New Candy method here, the case structure works just fine. We can reuse most of it, but maybe instead of giving priority to specific candy types, we can add a bit of randomization for variety. The common candy machine could pick from a broader set without the extra rules we had in the picky machine.
Ooh, that randomness could be fun. Just like how the greedy machine pumps out more candy than you need, but not quite that extreme. What if we adjusted the quantity output too so it gives a bit more than average?
Yeah, good point. Common consumers will want a solid handful of candy, so a few more grams could add to the experience. We could tweak the candy creation process by increasing the amount, depending on the type, but still keep the selection general.
I like it. We'll adjust the weights on the candy amount in gram depending on the candy type but not go overboard. And just to keep it smooth, if we ever add new candy types, this machine will be flexible enough to adapt without needing changes in the core structure.
Exactly. Let's also keep in mind the memory management issue we talked about in the picky machine. We can reuse the return, candy equals 0, check here to handle any memory allocation failures safely. Clean and efficient.
And that's it. A machine for common candy lovers that's simple, randomized for variety, and outputs just the right amount of sweetness. Classic.
Yeknum watch. I did something while you were at the candy shop.
Nice, Ajnin. This abstraction is really going to help streamline our Candy Machine system. By using a CandyMachineProvider, we're centralizing access to the Candy Machines, and I love how you're reusing the same default Candy Machine across all instances. Talk about memory efficiency.
Exactly. The var_stat for the default Candy Machine ensures that there's only one instance of the common Candy Machine shared across all providers. That way, we avoid creating a new instance for each consumer, saving both memory and initialization time.
And the custom Candy Machine being a reference? Clever. If the provider ever needs a specialized Candy Machine, we just hook it up through this reference. Otherwise, we fall back to the default. Flexible and efficient.
Right. The GreedyCandyMachine method does the heavy lifting here. It checks whether a custom machine is provided. If not, it simply returns the shared default Candy Machine. This keeps things simple for consumers who don't need anything special but allows us to plug in a custom machine when required.
And with the isValidref check in place, we can be sure the custom machine is valid before using it. No nasty null pointer surprises. This makes the system resilient.
The key here is keeping it dry. Don't repeat yourself. We centralize the logic for selecting machines, and by using a shared default Candy Machine, we reduce redundancy. But when needed, we have the flexibility to handle special cases.
This setup also future-proofs us for new Candy Machines. If, say, we create a deluxe Candy Machine or something fancy, we can easily slot that in as a custom Candy Machine for specific providers without touching the default flow.
Exactly. New Candy Machines just need to implement their own getNewCandy logic, and the provider will handle the rest.
Looks like we're ready to satisfy all kinds of candy cravings with minimal overhead. Simple consumers get the default machine, and picky or greedy ones can have their own special setups. Sweet. Alright, here we go. Let's integrate the NinjaIncCandyMachineProvider to handle 3 different types of candy machines: greedy, picky, and the usual consumers. The magic will happen in FB_init where we set the custom candy machine based on the Ninja's consumer type.
Sounds solid. First we declare 2 instant variables, GreedyMachine and PickyMachine. By extending the CandyMachineProvider, we inherit that nice getACandyMachine method and can now dynamically assign the right machine based on consumer types. The FB_init method is perfect for this since it's called when the function block is initialized. We can easily set the right machine up front.
Exactly. The case statement handles the different types of consumers. For greedy ninja monkeys, we assign the greedy machine, and for picky ones, it's the picky machine. And if it's a regular consumer, we just fall back to the default candy machine, thanks to our parent class.
Good use of inheritance here. By only overriding the initialization behavior in FB_init, we don't need to mess with the underlying logic of the getACandyMachine method. That way, the provider stays flexible and reusable for any future consumer types NinjaIncCorporated might add.
And it's efficient, too. We keep the default candy machine shared across all providers, while the greedy machine and picky machine are instance-specific but only created when needed. This strikes a nice balance between memory use and functionality.
Exactly. One small thing, since custom Candy Machine gets initialized in FB_init, it won't change dynamically afterward, right? That's perfect for this design. Once the machine is set based on the consumer type, it doesn't need to switch mid-operation.
Right. No dynamic switching here, just a one-time setup during initialization. But it gives us the flexibility to expand in the future, should Ninja Incorporated decide they want more Ninja-specific candy machines. We could add new consumer types to consumer types without needing to refactor the core provider logic.
Exactly. The system stays open for extension but closed for modification. A perfect setup. Great work, Enums. Ninja Incorporated now has a robust Candy Machine provider that respects each ninja's cravings while keeping things efficient.
Yep, whether they're greedy, picky, or just plain candy-loving, we've got their candy cravings covered.
Alright, Enums, we're taking it up a notch. Now, we'll create the IndividualCandyPreferences abstraction. This is a simple interface that will allow each ninja to have their own candy preferences. But for now, it's just an interface. No logic, no data. Pure abstraction.
Gotcha. This gives us a clean way to define how each ninja evaluates their candy without locking us into any specific behavior. The method "how is the candy" will tell us how tasty a candy is, based on its type. But each ninja gets to decide their own rules, right?
Exactly. This method will return a TasteScale value whether the candy is disgusting, okay, or delicious. But the actual logic for determining that will be implemented by the specific preferences of each ninja.
Nice. And by keeping it abstract, we're saying that every ninja must provide their own implementation of how is the candy. This forces each ninja to have their own taste profile but lets them do it however they like.
Exactly. It's a classic case of enforcing flexibility while keeping the design open for future additions. If Ninja Incorporated decides to add more ninja types, we just create new classes that extend individual candy preferences without touching the space abstraction.
Clean, simple, and ready for ninja-level customization. Looks like we're building a truly flexible candy system here.
Yep, and by decoupling the preferences from the candy machines themselves, we keep things nice and modular. Great foundation for future expansions.
Okay, Ajnin, now we're diving into the Ninja Candy consumption behavior. This AbstractNinjaCandyConsumeBehavior defines how a ninja monkey loots a candy machine and how their satisfaction level is calculated when they munch on candy. We've also made it flexible enough to allow custom candy machine providers. Let's break it down method by method, ninja style. First we declare the abstract function block. We have one variable called CandyMachineProvider, and one static variable called DefaultProvider.
Now we add the FBinit, this one's straightforward. FBinit handles the initialization of the behavior. The important part here is the CandyMachineProvider. We're allowing the possibility to inject a custom provider, which gives us flexibility to use specialized candy machines when needed. If no provider is passed, we fall back to the default provider, which is the NinjaIncCandyMachineProvider.
Yep. The check with this validref ensures that we only assign a custom provider if it's valid. If someone passes null, we're safe, and we just stick with the default. Super handy when dealing with ninjas who don't have time to set everything up manually.
The next method is called Calculate Satisfaction Level. As input we declare tastiness and amount of candy. And the in and out variable is the actual satisfaction level.
This method is all about how satisfied a ninja gets after eating candy. It's abstract, so the actual logic is left for specific ninja behaviors to define. We take two inputs here, the tastiness of the candy and the amount of candy eaten. The satisfaction level gets adjusted based on those values.
Right, the amount of candy consumed and how good it tastes will influence how happy the ninja is. But the details of that calculation will differ depending on the type of ninja, so we leave this method abstract. This gives flexibility for different behaviors to calculate satisfaction in their own way. Now for the main event, loot a candy machine. This is where a NinjaMonkey goes to town on a candy machine. As input we declare a variable called consumer, and one for the preferences. In the var section we declare candy to eat, the candy machine and a variable named candy. First, we pass in the consumer, which is a reference to the NinjaMonkey, and optionally, their preferences for certain types of candy. If no preferences are given, we assume the Ninja will eat whatever they can get their hands on.
The interesting part here is how we handle the preferences. The key bit is this line. The and then operator is what's cool here. Normally, if you tried to check the preferences and they weren't valid, you'd get an exception. But and then ensures that the second part of the condition, checking the tastiness, only happens if the preferences reference is valid. No exceptions, just smooth ninja moves.
Exactly. If preferences are given, the Ninja will skip over candies that aren't delicious according to their taste. If no preferences are set, they'll happily eat anything. After that, the method fetches the candy from the machine using getNewCandy, checks if it's valid, and if it is, the Ninja eats it.
And if they like it? Well, candy.eatMe, consumer, takes care of the actual consumption. Each candy will have its own eatMe method, which handles how it's eaten. This keeps the candy consumption process abstract and flexible, so different types of candy can behave differently when consumed.
The loop runs through all the candy types, from candy bars to sour candy and the step size candy to eat to count binary, so the Ninja gets a chance to loot every kind of candy available in the machine. It's a full-on raid. But only if they like what they find.
So, to recap. FB init sets up the CandyMachineProvider. Either custom or default. Calculate satisfaction level is an abstract method to figure out how happy the Ninja gets after eating candy, with details left for specific Ninja behaviors to define. Loot a candy machine is the candy raid method. It handles the logic of how the Ninja loots the candy machine, checks their preferences, and eats the candy if it's tasty enough.
This setup keeps everything modular and flexible. Different types of Ninja candy consumers can define their own satisfaction logic, and the and then operator keeps us safe when checking for preferences. Plus, the default provider means we always have a fallback in case a specific machine isn't set.
It's Ninja-level candy looting. Efficient, flexible, and tasty. Alright, Ajnin, here's our CommonNinjaCandyBehavior. Nothing too fancy about this one, it's for the average NinjaMonkey. The key thing here is how we calculate the satisfaction level when they eat candy. We use a logarithmic function to model it because, as you said, the fifth candy won't make you as happy as the first.
Exactly. Let's go step by step through this method, calculate satisfaction level, and see how it works. First up, the inputs are the candy's tastiness and the amount of candy consumed. These values will influence how much we adjust the Ninja's satisfaction level, which is passed in as actual satisfaction level.
In the var section we declare the following variables. PickyScale, satisfaction relationship, gradient and amount relationship. As constant variables we declare, max satisfaction of satisfaction level in % equals 100, avoid division by 0 of satisfaction level in % equals 1, greediness of satisfaction level in % equals 79, max amount of candy amount in gram equals 500, logarithm base of type real equals 6.359. The tastiness comes from our TasteScale disgusting, okay, or delicious. The amount of candy is the quantity consumed, and this plays into our logarithmic formula later. Now, on to the actual calculation.
First, we set PickyScale. This value represents how much the Ninja cares about the tastiness of the candy. If the candy is just okay, we use its taste value directly. But if it's delicious, we give it a boost by using that value instead. Here's how we set it up.
Nice touch. This way, delicious candies get a little more love, while okay candies still contribute but not as much.
Next, we calculate satisfaction relationship. This represents the difference between the current satisfaction level and the maximum possible satisfaction, max satisfaction, which is 100%. We use 2 real to convert it to a real number for the logarithmic calculation. And, to avoid division by 0, we limit the lower bound using avoid division by 0, set to 1.
Right. This makes sure the current satisfaction never exceeds the maximum, and if it's 0, we treat it as 1 to avoid any nasty math issues. Now for the logarithmic part. We calculate gradient, which is the result of the logarithmic function. The logarithmic base is a constant, logarithm base, which we've set to around 6.359. This ensures the rate at which satisfaction increases slows down as it approaches the maximum. The more candy you eat, the less happy you become with each bite. That's what makes it realistic. The first candy brings a big satisfaction boost, but the more you eat, the smaller the boost gets, just like with burgers or candy. Then we calculate amount relationship, which is how much candy the ninja has eaten relative to the maximum amount allowed, the max amount. This makes sure the satisfaction is proportional to how much candy they've looted. This keeps things scalable. If they eat a tiny bit of candy, they get a tiny bit of satisfaction. But eat a ton, and their satisfaction grows, although logarithmically. Finally, we update the actual satisfaction level. We combine the gradient, amount relationship, and PickyScale to calculate the final satisfaction boost. The product is scaled by a factor based on the difference between the maximum satisfaction, max satisfaction, and a constant greediness, which we've set to 79. This keeps greedy ninjas from getting too happy too fast. It's also why delicious candy has a bigger impact. It gets multiplied by PickyScale, giving it a stronger boost. But even then, thanks to the logarithmic growth, the satisfaction level plateaus after a certain point.
That's pretty much it. We ensure the ninja's satisfaction increases based on the candy's taste and the amount eaten, but in a diminishing return style, thanks to the logarithmic function.
Yep, this design makes sure that a ninja can't just eat their way to maximum happiness, unless they really take their time and savor the delicious stuff. And with the max satisfaction and greediness constants, we can easily tweak how much satisfaction a ninja can get.
It's a simple but effective behavior, perfect for the common ninja monkeys. They loot the candy, they eat it, and their satisfaction gradually grows up to a point.
No extreme sugar rush, but enough to keep them coming back for more.
Now we create the PickyNinjaCandyBehavior. As var stat we declare the Picky default provider. It's a provider with the consumer type Picky.
In the calculate satisfaction level method we add some variables.
This method calculates how much satisfaction the Picky Ninja gets from eating candy. The formula is similar to what we've used before, but here, the picky scale is directly tied to the tastiness value.
Right. Picky ninjas don't just eat anything. They only care about candy that meets their standard, so picky scale comes directly from the taste scale. If the candy is okay, it gets a smaller boost. If it's delicious, it adds more satisfaction.
The rest of the calculation is straightforward. Satisfaction increases logarithmically, and we factor in the amount of candy eaten and the ninja's pickiness.
Nice and simple. Picky ninjas get less satisfaction from okay candy and more from delicious candy, but even then, it tapers off as they eat more. Just like a true picky eater. Now we work with the FB-init method.
Here's where things get interesting. We override FB-init from the base class, but we still call the parent class's version first. That's important because we want the base class to handle setting the CandyMachineProvider first.
And the Picky default provider is specific to Picky ninjas, so if no custom provider is injected, we'll use NinjaIncCandyMachineProvider with ConsumerTypes.picky.
Exactly. The order works out perfectly here. We first set up the base class's default behavior and then layer on the specific behavior for Picky ninjas. Now we create the GreedyNinjaCandyBehavior. We also declare a static variable in this FB, this time the GreedyDefaultProvider. And we need some constant variables in the calculateSatisfactionLevel method as well. The greedy ninja's satisfaction is calculated a bit differently. They get satisfaction from pretty much any candy, so we don't need a picky scale. Instead, we just use a logarithmic formula that considers the amount of candy they eat.
Greedy ninjas don't discriminate. They love it all. So we skip the picky scale and just go straight into adjusting satisfaction based on the amount they eat and how far they are from maximum satisfaction.
The logarithmic curve here ensures that satisfaction grows fast at first, but then levels off as the greedy ninja eats more. It's a nice way to model diminishing returns.
Now let's implement the logic in the FB init.
Just like with the picky ninjas, we override FB init.
So, to sum it up, Picky Ninja Candy Behavior uses a picky scale to reflect how much a picky ninja likes the candy, and it calls the parent class's FBInit first, then sets its own default provider. GreedyNinjaCandyBehavior skips the PickyScale since Greedy Ninjas love all candy, and similarly uses the base class FBInit before adding its own default provider.
It's a great setup. The FBInit order works beautifully here, and we get specialized behavior for Picky and Greedy Ninjas while still keeping things flexible with the option to inject custom providers.
Now those Greedy and Picky Ninja monkeys are covered, no matter their candy preferences. Well, Ajnin. Our NinjaMonkey class has officially been born, and it's got everything a NinjaMonkey needs. It's final, no more derivations, keeping it clean and straightforward. The FB extends AbstractCandyConsumer. First we declare the attribute reflection.
Next we declare three variables: CandyBehavior, a reference to AbstractNinjaCandyConsumeBehavior, CandyPreference, a reference to IndividualCandyPreferences, and myName of type ConsumerName, with the attribute instance path and attribute noinit above it. And one static variable, default candy behavior of CommonNinjaCandyBehavior.
Now let's break it down method by method again.
The first method we create is the getTastiness method. It is protected and its return type is TasteScale. As var we declare CandyType of CandyTypes.
This method determines how the Ninja feels about different types of candy. It checks if candy preferences are set, and if so, it uses them to get the taste scale. If no preferences are provided, the Ninja assumes every candy is delicious.
This lets us plug in specific preferences per Ninja, or, if none exist, they default to loving all candy. Simple, flexible, and very Ninja-like.
The next method is the lootCandies method. The var input is a bool named execute. And as instant variable we declare execution edge of tc2 standard.rtrig.
This method triggers the looting process. It uses a rising edge, execution edge, to detect when the looting starts, and then hands control over to the Ninja's behavior by calling LoggerCandyMachine. The behavior will handle which candy the Ninja loots and eats, based on preferences.
This makes the looting process simple. You hit the button, execute, and if it's a rising edge, the Ninja raids the candy machine according to their behavior and preferences. The next method is the eat candy bars and other eat methods. So about the eating methods, rather than explaining every single candy type, let's just focus on one. For example, eat candy bars handles eating candy bars. It calls calculate satisfaction level on the candy behavior, passing in the tastiness and the amount eaten.
Exactly. This is double dispatch in action. The NinjaMonkey calls calculate satisfaction level, but the actual calculation depends on the candy behavior, which determines how the satisfaction changes. And it uses the getTastiness method to factor in the Ninja's taste preferences.
This pattern repeats for other candy types like candy corn and chocolate candy, so we don't need to explain each one. It's the same structure, just different candy inputs. You have to implement them all, to follow along with the project.
Now we declare the method, remove nodes from path. We need the attribute estimated stack usage equals 4096 here.
As var in out we declare path of type tc2system.tmaxString. The inputs are called, number of nodes to remove and delimiter, one variable, called found. And two constant variables called, nothing and no nodes.
This protected method cleans up the Ninja's instance path by recursively removing unnecessary project nodes. It helps shorten the path, making sure it's concise and usable for logging or display.
Yeah, it's not too flashy, but it's handy when dealing with long instance names. The method chops off nodes until we get something usable. Next, the name property. It is just a simple getter that returns the cleaned up Ninja name. It's what gives our Ninja monkeys their identity in the candy world. And finally the FB init, we declare two more inputs, NinjaCandyBehavior a reference to AbstractNinjaCandyConsumeBehavior, and CandyPreferences, reference to IndividualCandyPreferences. We also need two constant variables, the number of project nodes and the instance path delimiter.
The FB init is where we inject the candy consumption behavior and preferences for each Ninja. If no custom behavior is provided, we fall back to the default behavior, CommonNinjaCandyBehavior. And the same goes for the preferences.
Yep, we check if a custom NinjaCandyBehavior is valid and use it. If not, we just stick with the default. The preferences get the same treatment. And here's something cool, we also clean up the Ninja's name by removing unnecessary project nodes from the instance path.
Exactly. The remove nodes from path method strips out the extra junk, so we end up with a concise name that starts with PRG, keeping things neat for logging or tracking. That's it. Now our NinjaMonkey class is fully equipped. It has customizable behaviors, preferences, and a clean name. Plus, the loot candies method gets the Ninja in action, ready to devour all the candy.
Absolutely. Whether they're picky or greedy, our Ninja monkeys are good to go, armed with behavior and preferences to loot any candy machine in sight. Well, Ajnin, you've got some seriously refined taste in candy. I see you've created your own candy preferences, and it looks like you have some strong opinions about what's delicious and what's disgusting. Let's walk through your Ajnin's candy preferences.
The FB is final and extends individual candy preferences. This method defines how I personally rate different types of candy. It's pretty simple. Based on the candy type, I return a value from TasteScale disgusting, okay, or delicious.
I noticed you're not a fan of candy corn or gummy candy. In fact, they're straight up disgusting in your book.
Exactly. I've always been picky about those. On the other hand, candy bars and lollipops? Totally delicious. I've set the preferences to reflect what I actually like and dislike.
Let's break it down with one example from the case statement. For candy bars, you return TasteScale.delicious. This means when a candy bar is eaten, my satisfaction algorithm will kick in based on that deliciousness. And if it's candy corn? Well, satisfaction isn't even on the table, it's disgusting.
Exactly. It's all about the Ninja's personal preferences. The method just returns the scale for each candy type, and my behavior takes care of the rest.
It's a simple but effective way to reflect your Ninja preferences in the system. And since I'm just a greedy ninja monkey who'll eat anything, I don't need preferences at all. But it's good to know what you think is tasty and what's not.
Right. My preferences will guide the candy machine to give me what I want, while you'll just eat whatever's in front of you.
Absolutely. Your preferences add a personalized touch to the candy consumption, while my greedy ways just focus on quantity. Classic Ajnin and Yeknam.
Alright, let's set up our main program so that everything is in place to test our candy consumption behaviors.
In the var section we declare, greedy, of GreedyNinjaCandyBehavior and picky of PickyNinjaCandyBehavior, in brackets 0. For the candy preferences of Ajnin we declare, AjninsPreferences of AjninsCandyPreferences. And Yeknam as candy consumer with, Yeknam of NinjaMonkey, in brackets, 0, 0, Ajnin as candy consumer, Ajnin of NinjaMonkey, in brackets, picky, AjninsPreferences, and two variables of type bool, feed Ajnin and feed Yeknam.
We implement the following lines to feed the monkeys. Ajnin.lootCandies, feed Ajnin. Yeknam.lootCandies, feed Yeknam.
We've got your picky ninja preferences injected, and for me, I'm running with the default behavior to test it too. Nothing fancy needed there. It's all controlled by the rising edges of feed Ajnin and feed Yeknam.
Yep, when we toggle those flags in online mode, we should see the candy looting in action.
Let's run the test with you, Ajnin.
Yeah.
One thing's bothering me, the log messages. When we run the program, the ADS messages are printed in a random order, which isn't helpful for debugging.
Yeah, that's because ADS messages aren't synchronized well, especially when multiple events happen at the same time. We could definitely benefit from a simple logger to handle the output more consistently. We need a logger that ensures our messages are printed in a well-ordered fashion, maybe by sequence. In the next scene, we'll create that simple logger to solve the problem and get clearer feedback from our tests.
I agree. Testing the candy looting is fun and all, but we need to see what's happening in the right order to ensure our behaviors and preferences are working as expected. Time for some structured logging.
For now, though, let's run this test and see how our default behaviors perform for you, Yeknam, and how my preferences play out. Once we have the logger, we'll be able to troubleshoot any issues much more efficiently.
Alright, Ajnin, let's lay the groundwork for our logger. This AbstractLogger class will handle all kinds of log messages, from critical to debug, but for now, it's just an abstraction. No functionality yet, but it sets the rules for how the logging system should work. The AbstractLogger extends the any to arg converter.
Exactly. Let's get all the main methods in place: critical, debug, error, info, and warning. Each of these takes in a log message and handles it differently depending on the severity. Of course, being abstract means we haven't implemented the details yet, but this sets the stage for any concrete logger to follow the same structure. As input, every method gets a message variable of type tc2system.t max string.
I noticed you also extended any to tr converter here. That's a smart move because when logging, we might need to convert various types of data to arguments. This will let us handle those conversions if we want to log complex data types.
Exactly. By extending any to tr converter, we inherit methods for converting different data types into a common argument format, making it easier to log data from different sources. This keeps our logger flexible and ready for more complex use cases. Here's a quick rundown of the methods we've defined in this abstraction. Critical, for serious errors that need immediate attention. Debug, for low-level messages useful for debugging. Error, for non-critical errors that still need logging. Info, for general information about program execution. Warning, for potential issues that aren't full-blown errors yet. Run, this is a utility method that will likely be used to flush or process the log entries.
Now that we have this abstraction in place, the next step is to create a concrete logger that implements these methods. That'll help us ensure messages come out in the right order when we're looting candy machines.
Yes and no. Yes, this abstraction gives us the flexibility to create multiple types of loggers in the future, but for now, we'll keep it simple with a basic implementation. No, we do not directly proceed with the logger implementation. First we need to define a log message DTO for our simple ADS logging. Let's add a FB, it is called ADSLogMessage. I add the attribute enable dynamic creation to it. As variables I declare, message of tc2 system.tmax string and message type of dword. We also will add a FB init method and two properties, message and message type.
Nice and clean, Ajnin. This ADSLogMessage is just what we need to buffer log messages, but with some good access control, meaning once we create an instance, its contents can't be changed directly, just accessed through the getter methods. It's essentially a data transfer object, DTO.
Exactly. The log message and its type are set when the fbinit method runs, and after that, they can only be accessed through the getter properties. This ensures that once a log message is created, no one can modify it by accident, which is super important for keeping the integrity of our logs.
The fbinit method initializes the ADSLog message with the actual log content and its type mask. This is where we set the message and message type during creation.
Once those values are set, they're locked in. Any attempt to change them afterward would have to go through direct memory access or pointers, which is good for keeping things stable and reducing unintended changes.
These properties are read-only and give us access to the log message content and its type. No setters, so no one can mess with the values once they've been initialized.
Right. The getters make it easy to retrieve the values whenever we need to, but since we're not allowing modification after creation, it guarantees the log messages stay consistent.
This makes ADSLogMessage a perfect container for our log data. Once it's created, it's rock solid. The next step is to integrate these messages into our logger, which will buffer them and make sure they're processed in the right order.
Yep. With this DTO in place, we've got the foundation for a reliable logging system. Now let's move on to the logging logic itself.
Alright, Ajnin. We're building the ADSLogger step by step. This logger handles all our log messages in a buffered way and supports dynamic resizing of its internal buffer. The key elements here are the ring buffer for messages, and a delayed print mechanism to control the flow of log output. Let's get started with the core components. Messages. This is a pointer to ADSLogMessage, the actual messages we are logging. It's a double pointer to give us dynamic control and flexibility over memory, especially when resizing the buffer. Size, the current size of the message buffer. We start small but resize dynamically when needed. Read pointer and write pointer. These are used to track where we read from and write to within our ring buffer. The ring buffer operates circularly, so these pointers will wrap around using modulo operations. Min buffer size. The initial buffer size is set to 255, ensuring we have enough space to start logging.
This setup gives us a good foundation for dynamically managing the messages. The key here is ensuring that our buffer doesn't run out of space, which is why we'll implement the resizing mechanism.
This is a simple method that increments the buffer pointers, read pointer or write pointer, and wraps them around if they exceed the buffer size. It's essential for maintaining the circular nature of the ring buffer.
Exactly. This keeps the buffer pointers within the valid range and allows the buffer to operate like a ring when we hit the end. We start back at the beginning.
This property checks if the buffer is empty by comparing if the read pointer is equal to the write pointer. This property checks if the buffer is full by incrementing the write pointer and seeing if it matches the read pointer. This is critical for knowing when to resize the buffer. These properties help us manage the buffer state, whether we need to add more space or if we can just read the messages directly. This method adds a new message to the buffer. It first checks if the buffer is full or uninitialized. If so, it calls resize to expand the buffer. Then, it creates a new ADSLogMessage, adds it to the buffer at the current write pointer, and increments the pointer.
The double pointer to the ADSLogMessage gives us the flexibility to dynamically allocate memory for the messages and store them in our buffer. This is crucial when we run out of space and need to resize dynamically.
Now for the interesting part, resizing the buffer. When the buffer is full, we double its size. This involves copying over the existing messages while maintaining the order in the circular buffer. To double the buffer size, we start by calculating the new size equals this dot size multiplied by 2, and allocating memory for it. Copy the messages. We use memcopy to copy the existing messages into the new buffer. We handle the circular nature of the buffer by copying in two parts, first from the read pointer to the end, and then from the beginning of the buffer to the write pointer. Adjust pointers. After copying, we adjust the read pointer and write pointer to match their new positions in the resized buffer.
Resizing a ring buffer can be tricky, but here we handle it by calculating the positions carefully. After copying, we update the pointers to reflect the new buffer layout. This prevents any loss of data and ensures the buffer continues functioning smoothly.
This method prints the message stored at the read pointer. After printing, it deletes the message from memory and increments the read pointer.
This keeps the buffer clean and frees up memory after a message is printed, which is important for preventing memory leaks. The increment buffer pointer ensures we keep looping through the buffer correctly.
The run method processes messages in the buffer. It uses a 30 milliseconds timer, (TON), to ensure there's a delay between each message print, simulating a more controlled log output. This helps us avoid flooding the log system with messages too quickly.
The 30 milliseconds delay ensures the log output is serialized properly.
When the logger exits, we clean up everything. This method clears out the buffer, prints any remaining messages, and frees the memory.
The FB exit method ensures we leave no loose ends. It makes sure all messages are printed before the buffer is freed and the logger is shut down. This keeps things clean and avoids memory leaks.
And there we have it. A fully functional ADSLogger with a dynamic ring buffer, message queuing, and controlled output. This logger is ready to handle our Candy Machine logging needs.
Absolutely. With this logger in place, we'll have a reliable and orderly way of tracking what's happening in the system. Now we just need to integrate it into our candy-looting ninja monkeys. We do it again with a provider.
Ajnin. Now we're setting up our LoggerProvider. This class is responsible for providing a logger throughout the project. We allow the possibility to inject a logger, but if nothing is injected, we fall back to our ADSLogger. This design makes sure we only have one logger being used consistently across the whole project.
Exactly. And since logging is a core part of our system, we're making the injected logger static, so there's only ever one instance of the logger used, no matter where it's accessed. Let's go step by step.
We declare the variables. Injected logger, this is a reference to a logger that can be injected from outside. It's static, so if a logger is injected, all instances of LoggerProvider will use the same one. Default logger, this is the default logger, ADSLogger, that will be used if no other logger is injected. We instantiate this internally to ensure that logging always works, even if nothing is provided externally. Here's the FB init method. It takes an optional logger as input, the other logger. If a valid logger is provided and no other logger has been injected yet, we set the injected logger to this external logger. This ensures that we only inject one logger throughout the project.
Exactly. The and then condition ensures that we only assign other logger if it's valid and no other logger has been injected yet. This protects against overriding a previously injected logger.
Now for the core of this provider, the logger property. This is where we determine which logger to use. If an injected logger is available, we use that. Otherwise, we fall back to the default logger, ADSLogger.
This setup ensures that if no custom logger is injected, the system uses the default logger. The fallback mechanism makes logging reliable without any extra configuration. If a project doesn't need a custom logger, it will always default to our ADSLogger.
One logger. We ensure that only one logger instance is used throughout the project, either an injected logger or the default ADSLogger. Safe injection. The FBinit method allows us to inject a custom logger, but only if no other logger has been set already. Fallback. If no logger is injected, the ADSLogger will always be there as the default.
Exactly. This makes logging consistent and avoids any duplication or misconfiguration. Now we're ready to start using this provider throughout our project to ensure every NinjaMonkey's logs are captured in the same, orderly way.
And the beauty of it is that we can plug in any logger we want, whether it's the ADSLogger or something custom. Flexible, but always reliable.
Let's put the LoggerProvider in main, and set it all up to capture log messages when the ninjas loot candy. We're using the run method from the logger to ensure messages are printed with a controlled delay. It's a smooth setup. Simple, but effective. And yeknom, it's refactoring time, and we have to update the logCandyConsume method in AbstractCandy to use our new logger system instead of directly calling ADSLogString. This makes logging more consistent and flexible, and the messages will now follow our orderly structure thanks to the LoggerProvider.
We integrate the new logger by adding LoggingProvider, LoggerProvider, 0, in the var section. And in the implementation part we exchange this with this.
By using the LoggerProvider, we can now manage our log messages in a consistent manner across the whole project. We've centralized logging into one system, meaning we avoid the messy output we used to get with ADSLogString. Now all messages are logged with a 30 milliseconds delay, ensuring smooth, readable output.
And since we're calling logger.info from the LoggerProvider, we also get the benefit of flexible logger injection. If we ever need to swap out the logger, we can do it easily without touching the logCandyConsume method.
This refactor sets us up for cleaner, more maintainable logging in the long run. With this pattern, we can scale the logging system as needed, while keeping the code simple and reusable.
Yep, all the benefits of refactoring in action. Clearer logs, better control, and we're fully set to monitor how much candy our ninja monkeys are consuming. The last thing is to add Greedy in the main. And now let's run the thing. Woohoo, Ajnin. We've reached the final step. I've now officially got my GreedyCandyConsumeBehavior injected into my NinjaMonkey instance. With this, our main program is complete, and the project is fully set up.
Well, yeknom, here we are. After all these candy machines, Greedy, Picky, and Common, they're all based on the same AbstractCandyMachine. Each one dispenses Snickers, Skittles, and the rest of the sweet bunch, but with a different approach.
Right. And each machine has its own behavior. The GreedyCandyMachine throws all types of candy at you, while the PickyCandyMachine takes its time and gives you only the good stuff.
That's the beauty of inheritance. We've centralized the candy creation logic in the AbstractCandyMachine, and each machine tweaks it just a little for its own needs. No duplicated code, no headaches.
Yeah, it's like the perfect use case for abstraction. Each machine works with AbstractCandy, so if we ever need to change or add new candy types, we just adjust the specific machine's logic without touching the others.
And don't forget the preferences. Our Ninja versions, me, Picky as always, and you, the greedy one, are handled beautifully by IndividualCandyPreferences. Each Ninja can define their own cravings, and that gets passed into how we loot the machines.
Right. Your AjninsCandyPreferences class overrides how is the candy, making sure you know exactly whether a candy is disgusting, okay, or delicious. Me. I just eat whatever comes out.
The separation of concerns here is key. Candy creation happens in the machines, while candy consumption behavior, like whether we greedily or carefully eat the candy, is handled by separate classes like GreedyNinjaCandyBehavior and PickyNinjaCandyBehavior.
It's a solid design for sure, but I was thinking managing all these candy types in Abstract Candy Consumer might get messy as we scale. We could make it more modular when adding new candy types to avoid clutter.
Absolutely. If we plan on adding more types of candy, refactoring that part to be more modular would help. We don't want the factory to become too unwieldy.
But overall, we've built a pretty robust system. Abstracting the candy creation, separating preferences from consumption behavior, it's all well organized and ready for new features.
Yep. And next time, we'll level up even more when we dive into interfaces. They take abstraction a step further, allowing classes to implement multiple behaviors without being locked into single inheritance.
Oh yeah, interfaces give you the flexibility to define what a class should do, without worrying about how it gets done. Perfect for making our Ninja monkeys even more versatile.
For now, let's sit back and enjoy the candy we've looted. But to everyone watching, don't forget to subscribe and hit the bell for our next adventure where we'll break down interfaces and take flexibility to a whole new level.
And with that, it's time for a candy feast.